plan is maybe 20 minutes of notes in terms of isotopes and atomic structure, and then we're going to do an activity after that, okay? So let's jump into it. We already know the names of the subatomic particles. We went over this briefly yesterday with the different types of matter and parts of matter. So one of the things that you noted is that Dalton, what did he say about atoms? They were indivisible, meaning not divisible. We actually know that atoms are divisible in some way or form because we actually can eject protons and electrons out of parts of the atom. And then we also will be changing the identity of the atom, we'll be changing the charge of the atom. And if we change the charge of the atom, that's then not an atom necessarily anymore. We have a different term for that. We call it an ion. If we change the number of neutrons, we don't call it an atom anymore. We call it an isotope. So we're going to kind of use our language and our vocabulary a bit more today. So these are your subatomic particles. The things, and I had you guys pull out a periodic table because I want you to look at the periodic table and look specifically at the numbers on different parts of the periodic table so that you understand when you look at a number what it means. Okay, so pull out any periodic table will do. The yellow or the blank ones or the colored ones I gave you or the colorful ones you've already colored, doesn't matter. So when you look at the atomic number, let's go with copper. Look for Cu, it's in the middle of the periodic table. You see copper? Tell me what is its atomic number. What number do you think it is? 29, good. So it looks like this. That means that copper has 29 protons. Okay? So if you look underneath the Cu, it should have a mass. What is the average mass there? 63.55. Okay. Its mass is made up of two things that actually have mass. Well, two subatomic particles have mass. Also give you protons as one, neutrons are the other, okay? So 63.55 grams is what protons plus neutrons are equal to. So since we already know from copper's identity, its identity meaning its atomic number, we should know the number of protons. We should then be able to calculate really easily the number of neutrons. Okay, so what am I going to do? I'm going to take 63. I'm actually going to round that up to 64 because this is an average. An average is not a real thing. Okay, just like your GPA average, that's not your real grade in any class. You know, if you have a 3.5, 5, 6, 7, 8, 9, 10, whatever GPA, that's not your real grade in class. It's an average of everything. Same thing with isotopes. Their averages are represented usually as a decimal, not a real actual mass. So if I take that and I round it to 64, that's the total grams. How many neutrons do I have? So I want you to take 64 minus 29. You do it in your head or on a calculator. 35. Okay, so then you're telling me we have 29 protons and 35 neutrons. Okay, so we actually can whittle down to the parts of the atom very easily here. So let's say I'm looking at a neutral atom. The neutral atom has protons and electrons that are equal. Because if a proton gives off a positive charge and an electron gives off a negative charge, or they carry those charges, if I have equal amounts of those, then that overall atom is going to have a neutral charge. So if it's neutral, that's when I say protons are equal to electrons. So if I've got a neutral copper atom, how many electrons does it have? 29, right? So you should be able to easily determine that after you figured out the proton number. So the things start to change when we have charges. So charges are going to be due to differences in electrons. Never, ever, 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 ever do we change protons. Protons are, it's like DNA, it's like its identity. So if I change copper's protons away from 29, let's say I made it 28, that's no longer copper. Who is that? Who? Nickel, right, the one right back from it. So we can never touch its protons unless we're doing nuclear decay, which will come a little later. But for the most part, we never touch its protons. So it's only an ion if we change the electrons. So how would it become a cation? Cats, you know, the T here, that's going to be how you remember cat ions are positively charged overall. It's only going to be able to become a cation if it loses electrons because it's going to have a lack of negative charges. If you have a lack of negative charges, guess what? The positives win, and that's how you get more positives. Or that's how you get a positive charge overall. So let's look at magnesium. Look at magnesium. It's in the alkaline earth metal group. How many protons does it have? Protons. 12 protons, right. So if it has 12 protons, and it's neutral, as in this example here, how many electrons does it also have? If it's neutral, 12. Okay, the more participation, guys, I can get from you is better. So if it's 12 and 12 there, I know that in magnesium 2+, that cation, how many protons does it have? What? What did I say about protons? Stay the same, right? Do not change protons. They stay the same. It's the electrons that change. So do I have, how many electrons do you think I have? How would I go from a 0 charge to a 2+ charge? I have 10. I have lost electrons. I have lost 2 electrons. If I lost 2 electrons, do you see overall, I have 12 pluses and I have 10 electrons, or 10 negatives. 12 pluses, 10 negatives. What's the overall net charge? The protons win by 2. So that's why it leaves an overall 2+ charge. So remember, never change the protons. They're constant. It's only the electrons that are going to be changing here. Okay, so opposite of that are anions. Doesn't anion just kind of sound negative? Sounds like a negative Nancy. I don't know. So anion is a negative charged particle or an ion. So how many protons does oxygen have? Look at oxygen's number. 8. Okay, so if it has 8 protons and it's neutral, how many electrons does it have? 8 electrons. Okay, now I have an anion. How many protons does this anion have? Protons, yes, protons are the same. They stay the same. But you can see I went from a 0 charge to a -2. How do I get a -2? I have to add 2 electrons, so it's now going to have 10 electrons overall. And that 2, because the comparison between these two, 8 pluses and 10 negatives, the 10 negatives win. There's an overall net charge of 2 negative charges. So we are going to have to start to look at each of the subatomic particles and really easily compare them if needed, figure out who's more protons, who's more electrons, stuff like that. Okay, so with the one that we've not really touched yet is neutrons. Well, neutrons, they weigh something just like protons do. So the only thing that we really have to deal with is that one extra part of the square on the periodic table, which is the mass. So look at fluorine. Fluorine, it's in the upper right-hand corner. What is fluorine's mass? Mass is 19. Okay, so what does that mean? What do you know automatically about it? I'm sorry, not its mass. Look at fluorine, the number of fluorine, the atomic number. 9. What do you automatically know about fluorine because of its atomic number? 9 protons. Okay, so I'm actually going to use both of these, but I want you to see. We know that from its atomic number it has 9 protons. We know its mass is 19. We know the difference between mass and number of protons is the number of neutrons. So how many neutrons does it have? 10. Okay. Oops. You should be able to really quickly see that 9 and 10 make 19. Okay, so that's going to be how you figure out that last one for neutrons. Moving on. Okay, so you're going to be able to make up any different example, and you're going to be able to switch around, find out whichever proton, electron, neutron you need to know. So we're going to do that in just a second on a big chart. But let's talk about isotopes quickly. Literally, every single atom out in the world is technically an isotope. Now, most people are like, oh, an isotope has got, it's an atom with a different number of neutrons. Different than what? Like, comparatively, every single atom of that particular element, like let's say copper, for example, again, every single atom of that is going to have different number of neutrons, so they're all isotopes. Now, you might have a lot of them that have one particular number of neutrons, which is a larger group of that type of isotope. But the protons are the same, and the neutrons are different. And that's proton being the same just simply identifies the element. So if I have the same number of protons, that's going to give you the element's identity. And if I have a different number of neutrons, that's just going to simply change the mass. And we'll have to deal with that in terms of recording different number of neutrons. That's it. So you can see my example here of hydrogen. And hydrogen, I know it's hydrogen. I don't even have to look at these symbols here. I know it's hydrogen because what do I see in the nucleus? 1 proton. That's it. 1 proton. All the way. 1 proton here, here, and here. So I can also see in the nucleus what is changing. Number of neutrons. You can probably don't see it very well. There's an N, and N there. So there are 0 neutrons over here, 1 proton over here. So what's its mass? 1. Its mass is 1. That is indicated where on this little symbol form. You can look and see the difference, the different numbers occurring. So is it the top number or the bottom number? Who says top? Who says bottom? I'm talking about where's the mass noted here. Is the mass noted as the top number or the bottom number? Right. So the top number is the atomic mass. The bottom number, 111, what does that identify? Proton, which is the atomic number, which is its identity, right? The bottom number tells you who it is. Okay? The top number tells you its mass. And that's called an isotope notation. I'll go about that on the next slide too. Actually, it's right here. So I'll show you that again. But if you look across the board and you see 111, and I give you, like, let's call this element X, and I say, figure out who it is, guys. You're going to have to look at the proton number and determine that atomic number on the periodic table and see who it is. And then the mass is on the top. So this one's 2 because you have 1 proton and 1 neutron. This one's 1 proton and 2 neutrons. And that's why this has a mass of 2 and this has a mass of 3. These are actually combined with oxygen to make heavy water. Have you ever heard of heavy water? It's a different, it's water, right? It's just H2O, but it's a different mass than normal water because protonium, deuterium, or tritium are actually involved instead of just our normal hydrogen, which is actually protium. So hydrogen has different isotopes, and sometimes we call them different names. That's it there. All right, so there are 2 ways to denote the isotope. These are actually on the notes I've printed for you. Do you guys? Oh, I have them. Instead of giving you a folder, since you have a folder, I'm going to spell the chart for you guys, okay? So next up here, you can take on the paper. I'm just going to have a look one. If you need more, let me know. If there are extras, just come on the lab. Oh, and my absentee, my people who are absent, Eli and Jasmine, somebody take an extra paper for them and just write the name on it. Protons plus neutrons is that. Any extra guys? Or need any extras? Oh, you need one? Oh, we need one. Gotcha. One more? Okay. If there are extras, just lay them on the lab station. I'll get there. Okie dokie. So you guys see up there on the top where it says atomic number, proton number, or atomic number, mass number, charge. Circle this one. This is the one you will see most common, and it gives you 3 pieces, actually 4 pieces of information, all in one. But it looks like a puzzle. Sometimes you're not going to know which is which. So you absolutely have to remember the bigger number is the mass number, and it should make sense, right? The mass is consisting of 2 different subatomic particles. It's going to be bigger. It's going to be protons plus neutrons. Mass number. The atomic number is indicative of the number of protons. And that's straight from the periodic table. You should be able to tell a lot simply from that. So, how many protons does nitrogen have in this example? 7 protons. How many neutrons does it have? How do you know? Right, I actually can see the math problem here. I can say 15 is the total, 7 is part, 15 minus 7 is 8. It's nice, you set it up just to subtract. I don't know who did that, but I love it. Okay, so that's 8 neutrons. Knowing that nitrogen has a 3+ charge, how many electrons does it have? Who said it? Somebody? Okay, good. 4. How do you know that? Right, so you know that there's a 3 overall charge positive, meaning overall there's 3 more protons, but you can't change protons, so you just have to knock the electrons down until there is a difference of 3. Okay, so you can figure that out very quickly now. The second way, oh, I have it right here, so didn't see that. Okay, the second way to denote it is like this. That's not a negative sign, it's a dash. So uranium dash 238, that 238 is its mass. I don't necessarily have to tell you the electron, the proton number, do I? Where could you find that? Where could you find the proton number? Not looking here. Say again? I can look at the PTOE, right. I can look straight at the PTOE for the atomic number. And that's going to give me the number of protons. So how many protons does uranium have? It's at the very bottom of your periodic table, or close to the bottom of your periodic table. 92, good. So 92 is what its proton count is. How many neutrons does it have? So 238 is its total mass. 146? All right, 146. I just did that in my head. We're going to assume that's right. Okay. So 146 would be its neutrons because you did 238 minus 92. And I just did 138 plus 8, which is 146. Yeah. Okay. So we should be pretty comfortable with that. Let's look at the chart, which is on your paper right below these notes. And we're going to pick probably half of these and do them right now, okay? So work with me, have your tool out. You want to make sure that you are writing these things down. Some of you guys, I think, did really well with your notes last unit, and that served as a great study tool. Kudos to you. You guys did, your class did very well. But some of you guys did not take good notes, and I think that's a hurt you, okay? So I'm forcing you to take notes for a year, okay? So let's start with the easy one. Let's start with this one. Okay, let's start with hydrogen. Straight up hydrogen, nothing is given to us. So you should be looking at your periodic table. What is the atomic number for hydrogen? 1. Okay, immediately once you get atomic number, I want you to go straight to proton number. Okay, what is proton number? 1. Those should be filled out at the same time because that's indicative, I can't say that now, the proton number. What is the mass of hydrogen on the periodic table? 1.008, right? So I'm going to write that under the atomic mass because this is the one that's the average, 1.008. But I can't work with a decimal like that because all these things weigh, like mass of protons and neutrons, weigh 1. So I need to actually round that. So I'm going to round that to 1 for its mass number. And this is me just showing you I'm rounding to 1. I know it's basically 1, but what I'm showing you for you. So knowing the mass number is 1, well, how many neutrons does it have? Who said what? I heard it over here. 0, thank you, because there is nothing else there. Our mass is 1, our proton is 1. Mass number minus proton number gives us 0 for neutrons. There's no more space for that. Okay, do you see that it's a neutral compound? Hydrogen is neutral. So how many electrons should it have? How many electrons should it have? I'll start pulling my cards here. You guys help me. Help me out here. Why 1? Because it has to have the same number as a proton, because these two things are going to be equal when it's neutral. And it's neutral because there is no charge on it. Okay, next, what do we automatically know from the next one? Okay, so we see the positive charge, but tell me in terms of the particles up here. What do we automatically know? It's hydrogen again. So atomic number is 1, proton is 1. That's easy, okay. Atomic mass is still 1.008 because it's not changing it doesn't tell us a different mass. So that's 1 again. So what about neutrons? Same, because I take 1 minus 1, that's still 0. Okay, but this time I have a charge. It's no longer neutral. So what has changed? So have they gone up or down? Down. They've lost the only electron, leaving us overall a net positive charge because of that proton. Okay, let's look at little bitty on my sheet, sorry. It says sodium Na 24/11. All right, so looking at, I'm on like the 5th one down. Look at sodium in period, well actually, don't even look at the periodic table. What can you find in this little setup here to tell me something about our table? What's the atomic number? 11, right, the bottom number is the atomic number. That is 11, and you just told me immediately 11 would be also where? Protons, because the atomic number is proton number. Okay, what is the 24 telling me? Mass number here, 24. So we're not actually going to have anything in the atomic mass column, because that's only when we don't know the true mass of that isotope. This isotope of sodium has 24 as its mass. Okay, so how many neutrons? 13, because you're doing total mass minus 11. And I set it up this way so you could just go kind of math problem here, 24 minus 11, 13 neutrons. How about electrons? Why 11? And so there's no charge on that ion, or it's not an ion, so there's no charge. So there would be 11 electrons in addition to those 11 protons to neutralize each other. Okay, now that's over, guys. Let's go one up. Let's go to the oxygen one. What do you know? Shout it out. Atomic number and proton number is 8, and that's that lower number down there. What do you know about its electrons? Let's go straight to electrons right now. Hold on. They said negative charge. That means you got 2 extra negatives. So how many negatives would I have? 10. I would have 2 more electrons. So that's 10 electrons. Okay. So then what's my mass? 16, right? So the atomic mass is out. It's the mass number that is told to us in the isotope notation. So then how many of the neutrons? 8. That one's easy because it's 16 minus 8. Okay. Let's go down to one with a dash like this. Fluorine dash 37. What does that 37 mean? It's mass number. Good. I told you to denote that that dash means mass. So dash mass, that mass number is 37. So we can't find out anything else up here. Where should you be looking? Okay, so look at the PCOE chlorines in the halogen group. 17 is what? Atomic number and proton number. Okay, so what do you guys want to find next? You guys want to find neutrons next? Okay, so tell me how I figure that out. Subtract. Good. So mass minus 17 is 20. Right. There's 20 neutrons here because 37 minus 17 is 20. What else do I know then? How many electrons? Because it is neutral, right? 17 because it's neutral, and we don't need the atomic mass. All right. You guys tell me from the last, whatever, 6 here, let's do 2 more. Which ones? Which one? P1? Okay. So we're doing the phosphorus one. Phosphorus is in the non-metal area. It's kind of like in the middle of the non-metals. So we actually don't need to look through our table. Everything on these isotopes are right in front of us. Okay, so what do you guys want to do first? Atomic number is what? 15. So the atomic number 15 also tells us proton number is 15. Okay. What does the 32 tell us? Mass number. Good. So mass is in this third column is mass number. So let's immediately find neutrons now. So you did 32, right? Minus 15 gives us 17 neutrons to make up the rest of the mass. And then what does this 3 negative mean? 3 more electrons, right? That's how you get an overall negative charge. So how many electrons do I have? 18. What is this? Okay. How about let's jump up here. Let's do this calcium one. That one doesn't tell us a whole lot. So you're going to have to look at your periodic table, look for calcium in the alkaline earth metal group. So what is calcium's atomic number? 20? Yeah, 20. Good. So what does that automatically tell us? Its protons are also 20. Okay. What is calcium's atomic mass? Atomic mass on the periodic table. 40.08, right? So you're writing that in the atomic mass column because we need to round it to our closest isotope, which would be what? 40. So this is going to be round to 40. Okay, math is easy here. Mass is 40. Proton number 20. Neutron number 20. So it's not often we have them exactly the same, but you'll see it probably 3 times every now and then. How many? Do we have more or less electrons? Less. We've got 2 less, right? So how many electrons do I have? 18. All right, you guys are rocking this. Okay, so who feels on a scale of 1 to 10 you could teach this? 10 you could teach this. 1 you're like, teach what? I cracked myself up. Thanks. Okay, I see at least 2 hands for everybody. Okay, cool. I need to see that. We'll come back to do some more of these. Okay, so the last thing that I need to talk about is our average atomic mass, and this is. No, I have some examples down there, but I don't have the word for you. So just like we calculate an average in like terms of it's like a weighted average or GPA, for example, they look at the weight of the course, they look at the number that you got, and they do a weighted average by calculating kind of based off a percent. Okay, we're not going to do normal averages where you add up everything and you divide by 4, for example. We're going to do weighted averages. So that's what when I say weighted average, that's what I mean by relative abundance. Okay. So, for example, if I have, I'll show you this first, there we go. If I have a big bowl of water, okay, and I actually picked out every molecule of water, I've dissected it, looked at the oxygen and the hydrogen, and I could count up their masses, I could look at their masses. I would then compare those, that number, let's say I counted up this one with the mass of hydrogen being 1, and the oxygen being 16. I counted 99 of these out of 100 waters in my bucket. And then I counted out only one of these in all of my bucket. I would obviously say I have a much less abundant water 20 versus water 18. And so relative to the other one, I have a lot less of this one, a lot more of this one. Instead of saying less and more, though, we actually give it percentages. We say this makes up about 1% of all the water in the world, every water molecule out there. And this makes up 99% of them. And these are estimates right here. And that's what I'm going from, okay? So relative just means compared to your fellow isotopes or your fellow isotopes that you are representing. So we have to get their relative abundances, or I have to give you percentages. So sometimes you're going to count them out. Sometimes you're actually going to get a percentage for them. And so whenever I give you a percent, that is its abundance. So sometimes instead of saying relative abundance, I put a number to it, and that's called percent abundance. So the relative is just going to be more qualitative, and the actual percentage is more quantitative. So what we'll do is then after we get the percent abundance of that particular isotope, we're going to look at its atomic mass. That is actually given to us in the problem, and we're going to figure out its average atomic mass. You're like, whoa, we're figuring out the average. Fantastic. Well, that average, everybody's already figured out. It's on the periodic table. Every mass on the periodic table is from this calculation. So we need to learn how to kind of appreciate that and figure out where these numbers came from. Because those numbers on the periodic table, sometimes it's like copper, 63.55. There's no copper atom that exactly weighs that, because 63.55 isn't even a whole integer. And we know protons and neutrons, they weigh full integers of 1. So we need to figure out how did they get the average on the periodic table. Okay, so we're going to do like 1 or 2 questions, and I think these will be good. So we're going to put the percent with the mass of the isotope and then figure out the average. Okay, write down for me chlorine 35 and chlorine 37. And then write down their percent abundance. Write down their percent abundance. So chlorine 35 and chlorine 37, the relative abundances are over here and circled as well. So you guys have your calculators? Who needs a calculator? And then just hold that on. Okay, so all we do is that first step, we're going to change percent to its decimal form, and that basically just means divide by 100, so sweep the decimal back twice. And then we're going to multiply mass times the decimal percent. So I'm going to write decimal percent, I hope that makes sense. So we take our decimal, so instead of being 75.77, it's going to be 0.7577. This one's going to be 0.2423. We're going to multiply these together, and after that, we're just going to sum them. And that's it. 3-step process. It's not hard at all. Okay, so if we have 35 AMUs, what does AMU stand for? It's on your reading guide. Atomic mass unit. So a lot of times when we talk about things in grams, these babies are so tiny, it's even hard to talk about them in terms of grams because it would be a very, very small mass, which we instead gave them another unit, atomic mass units, because they're talking about the mass of an atom. So that's why we usually determine it, or usually call it atomic mass units, not necessarily grams. Okay, so multiply by 0.7577. Somebody tell me what that is. I gotta find my calculator. There it is. 26.5195. I'm actually going to stretch those out because it's not my final answer yet, okay? AMUs, atomic mass units. Second one, 37 AMUs times 0.2423. What you guys get? Nine, 6, 5, 1. AMUs. Okay. So once we get that, do write this down for yourself because that way I can verify your work. Add those together. So much you get. 35.4846. Okay. Okay. So then this would need to be rounded to 2 sig figs, basically. Well, you can see the 2 sig figs there. So you'll see that this is incredibly close to what we have on the periodic table, right? What is the actual atomic mass of chlorine on your periodic table? 35.45. Okay. So what we did for this example, I showed you the mass number. Well, the mass number is what we generally refer to as the mass, but the exact mass here, you can see is definitely going to round up to 37, 35, but this is the exact mass of one of those isotopes. So if we had used these numbers here, this actually would be a little hair lower, and so instead of being 48, it would be 45 most likely. Okay, so whenever we do this, I really don't mind if you use the mass number, but most of the time I'm going to give you the exact mass. So you'll just multiply your masses by your relative percentages, and then take your two numbers or multiple numbers and add them together. This is on your test, not this example. There are 4 isotopes in the one on your test. Make a star, put test, because you will have to do this. I just don't want you to forget how to do the process. Okay, and then you will record to sig figs and AMUs. AMUs is going to be what you use for that. Okay, so at the very bottom of your sheet, put a star on those 3 questions, because that's what you'll do after your activity. Those last 3, and I'll help you on one of them if you need it number 2. It's not a hard question. I want you to see the light before I show you the light. Okay. So we have a really quick activity. It's going to take you about 30 minutes, we have about 37 minutes left in class. It's called Benium. Okay. I used to do Candium, but Candy gets everywhere. We'll have a Candy lab later next week. So right now you have an isotope called Benium. There are 4 isotopes of Benium: pinto beans, black beans, and 2 surprise beans I can't remember right now. White bean, navy beans, and black-eyed peas. Okay, so what you're going to do is you're going to figure out the relative abundances, their individual masses, and then figure out the average atomic mass of benium. Okay, it's going to help you practice this process, and then that's it for today. Okay, so lab groups. So I told you I could do a new seam chart and lab groups. Boost your class, yeah. Okay. So do you guys see where you are? I'll scroll down just a second. You do not need goggles for this lab, but you will have to pull out the lab notebook, and it's called Benium. Okay, go when you're ready. You need a piece of paper. Scroll down. You might keep your library started now. Yeah, if you weren't here yesterday, please put your reading guide in the inbox. I may have missed it. Abby, I thought that we had an even number. Go ahead and group 11-9. I'm trying to delete your name. Sorry about that. I was trying to figure out who I was missing, actually. Thank you. Just a moment, Jessica.